Okay, so this is now the introduction to vector algebra. So this is where we get to apply the last lesson with some numbers, which I think helps make it make sense. So the first thing we're going to talk about is a position vector. So this goes along with the displacement vector. Specifically, a position vector usually starts at the origin. So that's where the O is in OP to then a point, P, like an XY coordinate. We sometimes write it, this is called column notation, where it's written vertically. And then you have I's and J's, which should be very familiar from when we were talking about complex numbers. Same thing, if we move into three dimensionals, you just add the Z plane and a Z coordinate and a K. So it would be IJK. So from here, if you are adding vectors, pretty straightforward. You're just combining like terms. So you're going to group things by the I's or the X's, and then group things by the J's. This is a the X coordinates and the Y coordinates. So what we end up doing, you can look at it in column vector form. I think column vector form helps just because it keeps you from accidentally combining the wrong things. So if you are prone to very simple mistakes, I encourage you to convert it to this column vector form. So if, for example, I have A is, let's say, 3I plus 2J, and B is I plus J. Just keep it super simple. So there are imaginary ones in front of that B term. If I were to convert these to vector form, to the column vector form, then this would be the same thing as 3, 2. And this would be the same thing as 1, 1. Now, the reason why I think this is easier is because when you set it up to add, you have 3, 2 plus 1, 1. There are no extra letters there for you to get confused about. So I just add straight across. 3 plus 1 is 4, and 2 plus 1 is 3, and that's my new vector. You can do it the other way and group your i's. So 3i plus 1i gives you 4i. I mean, that's totally fine. But I think it's a very easy conversion, and I think column vector is a lot easier to write in. Okay, multiplying by a scalar, super straightforward again. So this lambda is representing a scalar, which is just a real number. So if I have 3a, where a is equal to 2i plus 3j, so I would just multiply each of those numbers. So you could have 6i plus 9j. Or if you want to take the time to convert to column form, this is the same thing as 2, 3. I have to stop writing that like a fraction, sorry. As 2, 3, and you're multiplying it by 3, so you multiply the top and the bottom, so you end up with 6, 9. Whichever one makes more sense to you, you can do it either way. I think column vector is cleaner. So now let's combine those two skills by multiplying and adding, or multiplying and adding a negative vector. So here we have 5a plus 4j. So the very first thing I'm going to do is convert to column form. So a is the same thing as 3, negative 2, and b is the same thing as negative 1, 4. Now I'm going to multiply. I have 5a is the same thing as 15, negative 10. And then 4j, that should be 4b, sorry. 4b is negative 4, 16, sorry. And then we're just adding them together. So 15 plus negative 4 would be 11. And then negative 10 plus 16 is 6. So that's my final answer. Again, I think that this part of this unit is super straightforward. It's just a different look at algebra. Okay, moving forward. Now we can combine addition and the triangle law to find any component of the directional vector algebraically. So this is basically if they give you x and y coordinates. So you can find it from A to B without having to do the distance formula. So if I have A is 3, 1, and B is 2, 4. Sure. I have no idea if this is going to work out nicely or not. So I have the vector OA plus AB is equal to OB. That's the triangle law. And then you're converting that in the second line, they're solving it for AB. So AB is the same thing as B minus A. You always do terminal minus initial. So the ending point minus the starting point. So we would have 2 minus 3 and 4 minus 1, which is equal to -1, 3. Ta-da, magic. Okay, so now let's look at a little bit more of a slightly complicated, something that isn't just plugging in numbers. So in this case, we have a parallelogram and we're looking to find the coordinates of point C. I'm going to go ahead and write out more of my work just to save myself a little bit of time, and then I'll talk you through it. So what I started with here is just determining a couple of my known factors. Since they gave me a parallelogram, think back to the thing that we talked about with equivalence for parallelograms. So since there are the two diagonals from A to C and from D to B, we know that they have a shared midpoint. Therefore, we can use those equivalence relationships. So now I'm going to, since I know that they are equivalent, I can solve, oops, goodness gracious. I can solve this pretty easily. So I have 5, -1 is equal to or equivalent to -x, 2 minus y. And these are basically two separate equations. So that would mean that x is -5 and y is 3. So now I have my coordinates. So in order to write them in the same way that the problem did as coordinates, I would say that the final answer is -5, 3. So that's your final answer. That's an example of not what I would call a complicated problem, but something that's a little bit indirect that IB might throw at you. Okay, so next we're gonna touch on magnitude. So magnitude, again, is the length of the vector. So if you're given the components of the vector in column form, then you can just go ahead and square each component, add them together, and put them under the square root. This is the way the formula is written on your formula sheet. That's the way you'll see it. It does not give you the following formula for directional vectors, which is with x and y coordinates. But this is a formula you should know because it's just the distance formula. Now, hypothetically, if you were to have a 3-dimensional shape, the only thing you would add here is a third term where you have C2 involved as well. But you don't, so you're fine. But it's always going to be your x term minus your, your in term minus your initial term. So let's go ahead and take a look at this 2-dimensional example. So I need to make it so that the magnitude of C is equal to 2 times the magnitude of D. So I'm going to go ahead and plug that in. So I have C would be the magnitude of C would be equal to the square root of -7 squared. Make sure you have that in parentheses. That should become a positive 49 plus 6 squared, which would be 36. So this is square root of 49 plus 36, which is 85, I think, if I'm awake enough. And then this should be the same thing as 2 times the magnitude of D, where the magnitude of D, not a parentheses, would be equal to the square root of k squared plus the quantity of 2k squared. So since it's the quantity of 2k, that becomes 4k squared plus k squared, which is 5k squared. And then we're doubling that. So then I get that 10k squared is going to be equal to the square root of 85. And then you solve it for k. And wait, I missed something. Oh, sorry, the square root of 5k squared. And then you should, here, sorry. So you have 2 times the square root of 5k squared is equal to the square root of 85. I'm going to square both sides to make it prettier. So you get 24 times 5k squared, which is 20. So we get 20k squared equals 85. Divide by 20 on both sides, you get k squared is equal to 85 over 20, which simplifies to something over 4. 85 divided by 17. So 17 over 4. And then you take the square root of that. So then you should get plus or minus the square root of 17 divided by 2. And that's your final answer. It's the value of k. Cool? Very cool. Amazing. All right. Okay, so a unit vector is just a fancy way of saying that, sorry, can't focus. A unit vector is just saying a fancy way of saying dividing by the magnitude. It just means it has a length of 1. So I don't believe that these formulas are on your formula sheet, but if they said convert this to its unit vector form, then you should be able to do it. Okay, so I'm going to post some additional IB work and the Delta Math, and you should be good to go.